A small black tile survives with a galaxy etched at its center, and a contour around mass that no eye could ever see. Then, Euclid launched, and astronomers began doing something close to impossible, mapping the dark universe through distortions smaller than a human hair seen from kilometers away. If those maps are finally good enough, do they confirm cold dark matter, or expose that our invisible scaffolding has the wrong shape? The clue on the lensing plate is almost rude in its simplicity. Light here, mass there. That split is the whole modern problem of dark matter. We do not infer it because telescopes missed a faint glow. We infer it because gravity keeps refusing to add up. In galaxy clusters, in spinning galaxies, in the bent paths of light itself, the visible matter falls short, by a lot. The question now is no longer whether unseen mass exists in some form. The question is whether we can map it well enough to test the model we built around it. Euclid launched in July 2023 for one reason that matters here: to measure weak gravitational lensing across an enormous stretch of sky. Weak lensing is not the dramatic ring or giant arc you see around a cluster. It is subtler than that. A foreground mass nudges the shapes of many background galaxies by tiny, coherent amounts. One galaxy is noisy. Millions become a map. By late 2023, Euclid's first images showed the mission's optics were stable across a wide field, in visible and near-infrared light. Exactly the kind of stability you need when the signal is almost insultingly small. By 2024, its first scientific fields were already delivering millions of galaxies, clusters, and lens candidates. So, the promise changed. Dark matter was no longer just a missing mass argument. It was becoming geometry. That is the question of this episode. If Euclid helps build the first high-fidelity maps of the dark universe, what exactly can those maps settle? Can they tell us cold dark matter is basically right, with galaxies and gas doing the messy part? Can they reveal halos that are too smooth, too round, or too weakly clustered for the standard picture? Or will the real lesson be harsher, that measuring the invisible is so difficult that the bottleneck is not theory, but calibration? And there is one more complication. People hear dark matter map and picture a clean, three-dimensional portrait of the Milky Way. That is not what Euclid directly gives us. Our own galaxy's dark halo is still mapped mostly through motion. Stars, streams, globular clusters, satellite galaxies, especially with Gaia. Euclid's revolution is larger than the Milky Way, and less simple. Here is the principle. Mass bends space-time. Light follows that curvature. So if a sheet of matter sits between us and distant galaxies, those background galaxies arrive at our telescopes slightly stretched and slightly aligned. Not enough to notice by eye. Typical weak lensing distortions are tiny. A statistical fingerprint buried under the fact that galaxies already come in every shape imaginable. So astronomers do not trust one galaxy. They trust populations. They measure shape, orientation, color, distance estimates, instrumental blur, detector effects, and then ask whether many galaxies across one patch of sky lean the same way. If they do, gravity has left a watermark. That is why Euclid matters. It was built to do this repeatedly, precisely, and across about 1/3 of the sky. And if you've enjoyed this story so far, subscribe to future archives. There's another mystery on the way. Euclid did not begin this story. DES, KIDS, and Subaru's Hyper-Suprime Cam already pushed weak lensing into precision cosmology. Those surveys improved matter clustering measurements and built increasingly useful maps. They also taught the field where the traps are: shape noise, atmospheric blur for ground telescopes, intrinsic alignments, where galaxies line up for reasons that are not lensing at all, photometric redshift errors, where you misjudge distance and therefore misjudge what mass sits in front of what light. In other words, before Euclid could challenge dark matter theory, the field had to learn how easily a fake universe can emerge from subtle bias. That matters because some of the most interesting tensions in cosmology are not giant contradictions. They are slight, persistent mismatches in how clumpy matter seems to be. Small error bars can change the story. Biased error bars can invent one. Cold dark matter earned its status because on large scales it works astonishingly well. In simulations, matter collapses into a cosmic web, Filaments, knots, halos within halos. Galaxies grow inside that scaffolding. The model explains a huge amount of the universe we observe. But success on large scales does not end the case. The real pressure is on smaller scales. How many low-mass subhalos should surround a galaxy like the Milky Way? How steep should a halo's inner density become? How closely should visible galaxies trace total matter? A better map does not tell you the particle's name. It tells you whether the particle, whatever it is, behaved in a way that made structure clumpy, cuspy, and hierarchical, or softer than expected. So, the first use of Euclid is brutally practical, not what is dark matter, not yet. Did dark matter build the universe in the pattern our standard model predicts? Here the story narrows, and gets trickier. The phrase map of the Milky Way's dark matter sounds as if one telescope can simply photograph our halo. It cannot. We live inside the system we want to map. We do not get the clean external view we have of other galaxies or distant structure. So, for the Milky Way, the strongest evidence still comes from dynamics. Gaia measures the positions and motions of more than 1 billion stars. Tidal streams, the shredded trails of small galaxies and clusters, curve through our halo like thrown ribbons. Their orbits respond to the underlying gravitational field. If a stream bends one way, flares another, or contains gaps that can hint at the halo's shape, and sometimes at subhalos passing through it. So Euclid is not replacing Gaia. It is setting the Milky Way inside a larger cosmic context. The local halo and the grand dark web are parts of the same theory. If one looks wrong, the other may explain why. Now, the scientific dispute sharpens. Suppose a halo looks smoother in the middle than a simple collisionless cold dark matter simulation predicted. That sounds like a dark matter problem. It may not be. Stars explode, gas falls in, cools, and gets blasted back out. Black holes inject energy. Over billions of years, ordinary matter can stir the central gravitational potential enough to reshape the dark matter around it. This is called baryonic feedback, and it is one reason small-scale tensions are so hard to read. The same observation can support two different stories. Either dark matter behaves differently from the standard picture, or normal astrophysics is more disruptive than early simulations captured. That is why no honest map is just a map. It is a confrontation between measurement, simulation, and messy galaxy formation. There is another possibility. Maybe the map really does come out too smooth. Warm dark matter would erase some small-scale structure, because faster-moving particles in the early universe would not clump as easily. Self-interacting dark matter would let dark matter particles scatter off one another, softening dense centers and sometimes producing rounder inner halos. Those ideas are not fantasy. They are active alternatives designed to match observations that simple cold dark matter handles awkwardly. But they pay a price. Change dark matter's behavior too much, and you spoil the large-scale successes of the standard model. The rival theories have to thread a needle, different enough to fix genuine anomalies, but not so different that they break the cosmic web, the microwave background, or cluster-scale lensing. That is why Euclid's maps matter. They can squeeze that parameter space from both ends. There is a third possibility, and it may be the least glamorous, but the most dangerous. The tension could live in the pipeline. Weak lensing is a triumph of statistics over intuition. You correct the telescope's blur. You estimate redshifts from colors. You model which galaxies made it into the sample and which did not. You account for galaxies whose shapes are correlated before lensing ever touches them. Then you compare all of that with synthetic skies built in simulation. At each step, tiny biases can lean in the same direction. If Euclid ends up changing cosmology by exposing those biases, that would still be a major scientific result. It would mean the invisible universe was not hiding only in space. Part of it was hiding in our analysis methods. And that creates a nasty question for the next decade. If multiple surveys agree, are they confirming reality or sharing the same assumptions? Even before the final maps arrive, Euclid has already changed the burden of proof. Its early releases showed dense fields packed with usable galaxies, survey-grade image quality, clusters, and strong lensing candidates. That sounds procedural. It is not. For weak lensing, clean optics are not a luxury feature. They are the experiment. If the point spread function drifts, If the detector subtly shears shapes, if the calibration slips across the field, your dark matter map inherits fiction. So one of Euclid's first achievements was almost philosophical. It demonstrated that a space mission could hold image quality steady over the wide field needed for precision lensing at scale. That does not settle dark matter. It settles whether this kind of measurement can be trusted enough to start the argument on stronger ground. Here is the reframe that matters most. The breakthrough is not a single dramatic picture of dark matter draped around the Milky Way. It is the merger of incompatible viewpoints. Euclid maps total matter statistically across cosmic history. Gaia maps our galaxy through motion. Rubin will add colossal time domain and wide field depth from the ground. Roman will bring high-resolution infrared survey power. CMB lensing traces matter using the oldest light in the universe. Each method is blind in a different way. Stack them, and dark matter stops being one image. It becomes an atlas, multi-scale, cross-checked, harder to fool. That is also why the stakes rise. A mismatch that survives all those probes is no longer one awkward survey result. It becomes a structural problem in cosmology itself. Now, we move from established science into informed speculation. One plausible future is almost disappointing in the best possible way. Euclid, Rubin, Roman, Gaia, and CMB lensing converge. The apparent mismatches shrinks once baryonic feedback is modeled better, calibration improves, and selection effects are tamed. The dark universe looks clumpy enough. Halo shapes land within the standard range. Cold dark matter survives its sharpest structural test. That would not make dark matter less mysterious. It would make the mystery narrower. The problem would shift away from cosmic structure and back toward particle identity. We would know more clearly how dark matter behaves gravitationally, while still failing to catch the particle in a detector or produce it in a collider. A better map, in that future, closes loopholes without closing the case. A second future is more disruptive. Suppose cross-checked maps still show fewer small clumps than expected. Suppose inner halos stay rounder or less cuspy after ordinary feedback is accounted for. Suppose lensing-based matter clustering remains weaker than some early universe inferences prefer. Then the invisible mass is still there. But it is not behaving like simple collisionless cold dark matter. That would push warm dark matter, self-interacting dark matter, or mixed dark sector models much closer to the center of the field. Not because they sound exotic, but because geometry would be forcing the issue. Galaxies would be telling us that the hidden scaffolding grew structure more gently than the standard picture allowed. That is the dangerous power of a map. Once the pattern is wrong, the crisis spreads far beyond one missing particle. The third future may be the most realistic in the near term. Euclid changes the field profoundly, but not by delivering a verdict. Instead, it reveals, in humiliating detail, how hard mapping the invisible actually is. Shared systematics, baryonic uncertainties, and model dependence remain large enough that every dramatic claim demands another cross-check. That is not failure. It is the mature version of science. In this future, Euclid's greatest gift is discipline. It forces cosmologists to compare surveys, expose hidden assumptions, and narrow which anomalies deserve to survive. Some apparent cracks disappear, a few get stronger, the field becomes less certain in its rhetoric and more precise in its method. Sometimes progress looks like a discovery. Sometimes it looks like eliminating the excuses that once made every interpretation sound plausible. So, the artifact at the center of this story becomes less mysterious once the science is honest. The lensing plate would not represent the moment dark matter was finally seen. It would represent a calibration culture, a time when astronomers learned to trust a map made from distortions, averages, redshift estimates, and repeated correction. Its etched blank contour matters because dark matter is not drawn from brightness. It is reconstructed from gravity. And that chipped metallic layer beneath the ceramic face suggests something practical, almost humble. This was a teaching object, or a check sample, from an era when the hardest thing in cosmology was not imagining invisible mass, but proving your inference pipeline had not bent the sky for you. What did Euclid change? It changed dark matter from a persuasive absence into a measurable pattern. That is enormous. But it is not the same as solving dark matter. The strongest version of the standard model may survive. A smoother than expected universe may point beyond it. Or the deepest lesson may be methodological, that the invisible universe is harder to measure than even good theories assumed. The artifact leaves one fair conclusion. A map can tell us where hidden mass acts. It can tell us how structure grew. It can even rule out whole families of models. It still may not tell us what the dark matter particle is. So, here's the real debate. Will Euclid's dark matter maps actually decide between cold dark matter and new physics? Or only show that the invisible universe is harder to measure than our theories assumed? Let me know in the comments.